Hi everyone, Dr. P here, and in this lecture video we're going to look at electron configurations of atoms. Now I'll start off a little bit with some background first, and then we'll look at the actual orbital energies. In particular for polyatomic atoms, and then we can look at the periodic table and electron configurations. Then at the end I'll summarize what we talked about. All right. So a little bit of background. Remember last time we talked about quantum numbers. Well, the fourth quantum number is the electron spin quantum number. M sub s. And this can be plus or minus 1/2, or we could call it alpha or beta, up or down. There's just two different spin states. Now, why is it called spin? Well, in classical physics, a spinning charge produces a magnetic moment. And these electrons do have magnetic moments. What's a magnetic moment? Well, it's like a little tiny bar magnet. You can think about it like that. So the electron has a magnetic property to it, so it behaves like a magnet. That's why electrons can be deflected by magnetic fields. Now, of course, an electron is not really spinning. Remember, an electron is a probability cloud of where we can find the electron. It's a probability distribution found in an orbital. So the electrons are not really spinning, even though they have a quantum mechanical property called spin. All right, so something important just to remember there. I remember in grad school having a big debate with my roommate about how, because he's a friend from college and he was a mechanical engineer, and so I was trying to explain to him nuclear spin of nuclei of atoms, and he was like, so they're spinning. I'm like, no, they have the property of spin, but they're not actually spinning. It's like, well, but they have a spin, so they're spinning. I'm like, no, they have angular momentum, but they're not spinning. It's like, well, how can they have? And he said, how could they have angular momentum if they're not spinning? And I was like, well, they just do. It's quantum mechanics. It's weird. So I'm sorry to have to introduce you guys to weird stuff, but I'll try to make it as easy as possible. Now, another piece of background is something that I mentioned briefly last time. I didn't say what it was, what it's known as, but it's known as the Pauli exclusion principle. Which is that in a given atom, no two electrons can have the same set of 4 quantum numbers. So we can't have the same set of n, l, m sub l, and m sub s. We could have the same n, l, and m sub l if our m sub s, our electron spin quantum number, is different. So the upshot of the Pauli exclusion principle is a given orbital can hold 2 electrons of opposite spin, or different spin. There are only 2 spin states, so it's going to be opposite spin. we'll talk more about this later when we start filling in our electron configurations. All right. Now, I mentioned before that the quantum mechanical model works well for hydrogen atoms, and I said in the last lecture video that it works pretty well for other atoms, although we have to make some approximations. So, for example, let's look at He atom. So we have a 2+ charge in the nucleus, and we have 1, 2 electrons. So we need to account for the kinetic energy of the electrons, the potential energy of the nucleus electron attraction, and the potential energy of electron repulsion, because they're two negative charges. Now we can't solve those exactly. Since the electron positions are unknown to arbitrary precision because of the uncertainty principle, we don't know exactly where the electrons are. Remember, they're clouds of probability. We can't calculate the repulsions exactly. So we make some approximations. But that's okay with what we do. So what we're going to do is we're going to pretend, when we start looking at our energies of our orbitals, we're going to pretend that each electron is moving into a field of charge that's the result of the nuclear attraction and the average repulsion of all the other electrons. Let me draw it out. So if we're going to talk about orbital energies, our assumption is we're going to treat each electron as if it was, oh, how should I say it here? Alone in a field of charge due to nucleus plus other electrons. So for example, in sodium, we would have 11 plus, and then we'd have some field here of 11 electrons. And so our outermost electron is repelled by 10 electrons, so it's not tightly bound. So it effectively sees a 1 plus charge. Those 10 electrons effectively screen it from the nucleus. So we'll say sees a 1 plus charge, not tightly bound. So the orbitals for polyelectronic atoms are similar to the hydrogen orbitals in what they look like. So, this is the 2p orbitals, all three of the 2p orbitals right here. But they're different in terms of energy. our orbital energy for hydrogen depends only on n. So for example, the energy of the 3s orbital is going to equal the energy of the 3p orbital, which will equal the energy of the 3d orbital. We say those are degenerate. For polyelectronic atoms, so anything other than hydrogen, there's actually an order. So we have the following energy values. So our energy for our s orbital at some given n is less than the energy of the p orbital for that given value, is less than the energy for the d orbital, is less than the energy for the f orbital. Okay, so E depends on n and L. All right, so it depends on the type of orbital. So in the end, what we get is a diagram that looks something like this. So for hydrogen, our energy is just determined by the energy level, 1, 2, 3, etc. So a 2s orbital has the same energy as the 2p orbitals. But everything else is going to look a little different. We will have the 1s with the lowest energy, and then we'll have 2s, and then a bit higher than 2s is going to be the 2p orbitals, and then we'll have 3s, 3p, and 3d. And then the weird thing is the 4s is actually lower in energy than the 3d. Okay, so that's something just to remember, that the energy of a n plus 1 s orbital is lower than the energy of an nd orbital. And this will make sense when we look at the periodic table. So let's go ahead and do that, and we can fill in these energy levels for a given element in the periodic table. And what we're going to use is what's called the Aufbau principle. We'll fill in electrons in orbitals starting with lowest energy and moving up. So we fill things in from the bottom up. So let's take a look at this then. Look at some examples here. Okay, so we have hydrogen. So hydrogen just has one electron. So we say 1s1. So it's superscript 1. And that means we have the 1s orbital and we have one electron. And we'll use a single-headed arrow here, just like a barb, like a fishhook or something. And we have 2s, 2p. Helium, we have 1s2. So we have our 1s electron, and we have 1s orbital, and we have 2 electrons in it. And so we draw in the second one with an arrow pointing in the opposite direction. Now we can then have lithium is 1s2, 2s1. Beryllium is 1s2, 2s2. And then boron is 1s2, 2s2, 2p1. So we just keep on going. Carbon is 1s2, 2s2, 2p2. Now what would this look like? Well, we've got our 1s, our 2s, and our 3 2p orbitals. So 1s2, 2s2, and 2p2. Now notice I put them in different energy or different orbitals here, and this is what's called Hund's rule. And Hund's rule states that it costs more energy to get the electrons to pair up than it does to put in another orbital. I like to say it as electrons spread out before they pair up. So then nitrogen is 1s2, 2s2, 2p3. Oxygen is 1s2, 2s2, 2p4. And this is a case where we now get pairing of our electrons. So there's our 1s2, 2s2, 2p1, 2, 3. Pair one of them up, 2p4. Fluorine is 1s2, 2s2, 2p5. And then neon is 1s2, 2s2, 2p6. Let me move those so you can see them. Sorry about that. Now if we keep on going, sodium, for example, would be 1s2, 2s2, 2p6, 3s1. Now you can imagine as we get bigger and bigger atoms, like let's say we had lead, that's a lot of orbitals we'd have to write out. So we do an abbreviation, noble gas abbreviation, where we say that the configuration of sodium is the same as neon with an additional 3s1 electron. These electrons in the outermost orbitals are called the valence electrons, and we'll talk about those more in the next chapter. Okay, so some rules to remember for filling orbitals. There's a particular order, that we have to fill our orbitals in. Okay, so it kind of looks like you can draw it sort of like a Christmas tree. So if I started out by saying, by drawing a 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 7s, 7p. So you start filling, you would draw an arrow going from the upper right to the lower left on this diagram. So I fill it going in this order, this way, and then I bring it back around, and then I go through my 2s, and then I bring it back around, and then I go through my 2p and my 3s, come back around, and now I fill my 3p, and then my 4s, and then back around, and then 3d. So 1s, 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, before I get to my 4f orbitals, before I fill those guys. And if you want to see a prettier version of this, this is figure 6.26 in the text. All right, so we've seen so far a bit of background so you can understand what's going on, how orbital energies work. And now, to wrap things up, I want to show you how this works in the periodic table. And for that, we're going to look at figure 6.27. I'm going to zoom in here a little bit more so you guys can see a little better. There we go. Just focus that. That's a little better. All right, there we go. Now this is illustrated, or this is colored in by blocks. And so what we have here are the S block on the left, these two columns, the P block on the right, and the D block in the middle. Where's the F block? Well, these guys here are part of the F, we'll say 2F block. I think if you look at figure 6.29, so I'm going to say see figure 6.29 for a little bit more information. And when I record the video on the periodic table, I'll talk a little bit more about that. But as we put in our electrons, we'll go ahead and fill up our orbitals here. So 1s1, 1s2. Then 2s1, 2s2, 2p1, 2p2, 2p3, 4, 5, 6, and now on to 3s. And so I can look at this, and if I remember, S block, P block, D block. Let me label that here. S block, P block, and D block. So that's my P block there. Sorry about that. S block on the left, P block on the right, and D block in the middle. So now I can use my periodic table to remind myself of the order of orbital filling, because I can just label these periods or rows, 1, 2, 3, 4, 5, 6, 7, and then I can just count over. So I know S block, so 1s1, 1s2. Next one, 2s1, 2s2, now my 2p's. Now my 3s, then my 3p's, then my 4s, and then my 3d's. So I can go all the way up to 3d. 3d10, and then I'm going to do my 4p's, 4p1, 4p2, etc. So figure 6.29 actually shows a good portion of these configurations. Let me just see, I don't have a copy of it here, but you guys can look at it. And it does show the F block as well. So that's one of the things that I like. You know, you could memorize this guy. Let me zoom out again. You could memorize this guy if you wanted to, the orbital filling diagram here. And you could use that to make a periodic table. Or you could understand and remember what the different blocks are in the periodic table, and then be able to figure out your filling order based on that. So go ahead and practice with writing out electron configurations. There are practice problems, and you'll do some more of that in the group activity. All right. So just to sum up again, we looked at some background and then talked about orbital energies. And in particular, I like this diagram here for everything else. And, you know I didn't draw it like that when I was drawing things here, just because I didn't want to take up that much room, because this starts getting bigger vertically. But this is an important diagram to be able to understand. And I forgot to label energy there, but you get the idea. And then lastly, we saw how things fit in with the periodic table. All right, well, thanks for tuning in. And in the meantime, stay safe out there. Bye now.